One of the reasons we tend to explore derivatives is because of their relationship with properties of functions. Specifically, we know that the derivative is utilized to work out the gradient at any given point of a function. More specific than that is that there are critical points of a function that can be looked at, namely turning points. That's for the first derivative, and we can use the second derivative to work out points of inflection and stuff like that. So in this video, we are going to have a look at a relative extrema. So remember that just simply means minimum and maximum points over a specific range of domain. The functions are going to have trigonometric components to it. So we can see here on the screen up there that we've got a function f of x equal to cos of 2x plus the cos of x all squared, which we write as cos squared x. And we're told that there's one relative minimum for x between 0 and pi. And we're asked to find the coordinates of this point. So that's what we're going to do. Let's get to it. We're trying to find a relative minimum, and that should scream out one thing to us, and that is find the derivative and set the derivative equal to 0. That's what we do for all functions to find maxima and minima. So let's do that first step. So let's just write solution. And we've got, I'll just start by rewriting it again, just easy if it's all together. F of x equals cos of 2x. So put the brackets there so we know that it's cos of all of 2x, not just cos of 2. And we've got cos squared x there added together. Remember that means cos x all squared. So f dash of x is equal to, and now we need to find the derivative of, well, we've got a plus, so we know the derivative is going to be the derivative of this plus the derivative of that. And this is made up of two functions, right? We look at an inside function. The argument to cosine is 2x, so 2x is effectively a function. And as a result of that, we do need to make sure that we are finding the derivative of the inside part. And then we look at the derivative of cosine. Okay, so the derivative of 2x is 2. So that's 2. And the derivative of cosine is negative sine. And so I need to put a negative outside and then sine, and we leave the 2x there. So this is using the chain rule. Chain rule says find the derivative of the inside function with respect to x. There's a 2. And then find the derivative of the outside function with respect to the inside function. So it's cos goes to sine and the negative, and then the 2x stays there. Similar sort of idea here, but just a reminder that cos 2x actually means, cos squared x actually means cos of x all squared. So the inside function is cos x, and the outside function is inside squared. So the inside function of cos x is, the derivative of it is negative sine x. And so that means that instead of adding, we're going to be subtracting sine x. And then the derivative of squared is 2. So I'm going to put a 2 here as well. And then I'm going to have sine of x. Oops, sorry. Let's say that again. Derivative cosine of x. So just to spell that out, then I'll erase it. I've got cos x all squared. And so the 2 will go down there. And then we subtract 1 from the power, so it's to the power of 1. And the interior just gets left the same, like so. So you've got 2 cosine x to the power of 1. We don't need to put the power of 1 in, so that can go. We don't need those superfluous brackets there. And so we have cosine of x and a 2 there. And then the sine of x and the minus comes from differentiating the interior bit. Okay, I'll get rid of all that. Now, we can't do anything, we can't simplify this in any meaningful way in this current form, because we've got a sine of 2x here, and we've got a sine x and a cos x here. So these are effectively different values, so there's no like terms there. And we really can't do anything more other than maybe taking out a common factor of a -2. But that's not going to be our best way forward. And the reason why is because what you need to get adept at is identifying particular patterns. And in this case, 2 sine x cos x has a particular pattern. We know it's a rule, we should do, and we should know that 2 sine x cos x is in fact exactly sine 2x. And so my next line is going to be minus 2 sine 2x minus sine 2x. Okay, so this bit, 2 sine x cos x, has been replaced with a double angle identity of sine 2x. Okay, now we've got like terms. We've got a sine 2x here and another sine 2x. We've got -2 of them here, minus another one here. So we've got minus 3 sine 2x here. So that has now been fully differentiated, plus it has also been simplified as much as possible. It's really important to simplify because it often makes subsequent steps easier to do. So in our case, we just need to be mindful of the fact that the name of the game is to find out the relative extrema. And that's found by setting the derivative equal to 0 in this case, for a particular domain. So let me start by saying that. So relative extrema is at f dash of x equal to 0. So what does that mean? It means that -3 sine 2x must be equal to 0. Cool. Now we're just going to solve. So we've got a negative sine 2x. So I'll divide both sides by -3, and that gets me sine of 2x is equal to 0, because 0 divided by -3 is just 0, right? So that's all right. And now you can sort of solve it from here however you wish, but I'm just going to do it the way I've shown you in class, which is this is between x and pi, because we were that's where we were headed with it. That's what we were told. So now I'm just going to say let theta equal 2x. So we've got sine of theta is equal to 0 for theta between 0 and 2 pi. So I've just multiplied the endpoints of the domain by 2 to get my new domain. Now I'm going to solve for theta. Now this is pretty straightforward. If you remember the unit circle, we should know where sine of theta is equal to 0. We're going to have sine of theta equal to 0 here, and then we're going to have sine of theta equal to 0 here, because there's no movement in the y direction, remember. So let's just go straight for it. Therefore, theta is equal to 0 and 2 pi, i.e. 2x is equal to 0 and 2 pi, which means x is equal to 0, because 0 divided by 2 is 0, and 2 pi divided by 2 is pi. So there are our two. I'm so sorry, I made a little mistake there. I can't be bothered redoing the whole video, so I'll just put it in here. This is so profesh. So the two solutions are 0 and pi. 0 and pi. Therefore, 2x equals 0 and pi, and x is equal to 0 and pi on 2. Pi divided by 2 is pi on 2. So that's okay, isn't it? Okay, so we've got our two solutions. We need to work out which one is going to be the relative minimum at that point. So there's a few ways we can do it. I'll just take it the first principles kind of way, not first principles, sorry, the first derivative way, which is to simply draw up a little table. And this is going to be x, and this is going to be f dash of x. And let me see, now we've got 0 and pi on 2, so I'll need to have a gap before 0, and then a gap after 0, and that's where pi on 2 will be. And then I need another gap after that, so I'll fill that in a second. Between 0 and pi on 2, I'm just going to pick a value which is pretty simple to work out. So I'm going to choose pi on 4, and I'll choose negative pi on 4, and I'll choose 3 pi on 4, which is just a pi on 4 more than pi on 2. Okay, we know that there is maximum or minimum at 0 and a maximum or minimum at pi on 2. Now, if I have a look at my my derivative here, -3 sine of 2x. So if I put in negative pi on 4, I'm going to have the sine of a negative angle. Don't even care what it is, but I know it's a sine of a negative angle. And I know from my unit circle, which how about I just draw one over here just for reference. I know from my unit circle that the sine of a negative value is going to be negative because it's in this quadrant where only cosine is positive. So the sine of a negative angle is going to be negative. Negative times a negative is a positive. A positive value for f dash of x means it's going to be going upwards. F of x is going to be going up. Pi on 4, that's going to be 2 times pi on 4, which is going to be a pi on 2. So that's going to be 1. So that's going to be multiplied by -3, which makes it negative. So it's going to go down. And then our next point is going to be 3 pi on 4. So that's going to be 2 times 3 pi on 4, which is 3 pi on 2. So it's going to be over here. So it's going to be a negative value. -3 times a negative value is going to be positive. So we're going to get this happening here as well. So we can see that we've got a maximum here, and then we've got a minimum here. And so we can conclude that, therefore, at x equals pi on 2, we have a relative minimum, or a local minimum, sometimes they're called. That's fine. The next thing we have to do is work out the y-coordinate, right? The x-coordinate is pi on 2, but what's the y-coordinate? It's not too hard to do. So we're going to take the original function, and we're going to substitute pi on 2 for x. So I'm going to say f of pi on 2 is equal to the cosine of 2 times pi on 2 plus cosine squared of pi on 2. Not too bad. The left-hand side gives me, sorry, the left-hand expression gives me cos of pi. 2 times pi on 2 is pi. And we've got cos squared pi on 2. Now, the cosine of pi is equal to -1. Again, looking at the unit circle here, cosine, there's pi there. It's -1 on the x-axis. So that's just -1. And then the cosine of pi on 2 here is going to be 0, okay, because there's movement on the y-axis but no movement on the x-axis. So that's just the cosine is going to be 0. And if we square 0, we get 0. So it's plus 0. So that's equal to -1. And just to squish it into this one slide here, I'll just put the coordinates over here. Pi on 2 is the x-coordinate, -1 is the y-coordinate. And just to be pretty, I'll put a red box around it so we can say this is the solution. That's basically it. So it's just a matter of using your understanding about derivatives and the role they play with functions in order to come up with your solution. Hope that was helpful. As always, ask questions if you're not too sure, and I'll certainly see you in class time to sort anything out if you need to. Bye!